just going to say a little bit more about the limb soup, right? So, so remember what the limb soup was. What is the limb soup? Right, you have some sequence. And how do we define the limb soup? How do we define the limb soup? Max, you were first. Go ahead.
The least upper bound of all of the limits of the subsequences.
That's right. That's right. So you let E be the set of subsequential limits, right? And then you let the supremum of that set you call the limb soup of the sequence. The limb soup of the sequence, and that could be infinite, right? It could be, could be infinity, right? It could be infinity. Okay, so we were in the middle of doing this thing that we call the characterization, right? Characterization of the limb sequences. And we said that, first off, that the limb soup was actually in the set of subsequential sequences, right? The limb soup was a subsequential limit. And two, for any number bigger than the limb soup, there was a point past which all values of your sequence were smaller than that greater number. Okay, and that any number, that there's only one number that satisfies this, right? There's only one number satisfying both of these properties. That is, if you have a number and it satisfies both these properties, then it must be the limb soup. Yes, Arya?
Do these properties have to be satisfied? So like for the second one, you just said that the limb soup could be infinite?
Yeah. So that's why I changed it to this phrasing rather than the x plus epsilon, rather than the limb soup plus epsilon, because if it's infinite, then the lim soup plus epsilon doesn't make any sense. But this one actually still makes sense if the lim soup is infinite. You'd say for any number bigger than that number, but in that case there is no number, right? So you don't have to worry about this condition. Yeah. Okay. Okay. So so let's do the proof of this. Okay. So let me call the let S star denote the lim soup. That's the bit. Okay. And let's just do the case first where S star is a real number. Okay. S star could be, positive infinity or negative infinity. Those actually turn out to be the easier cases to deal with. But let's look at the case where S star is actually a real number. Okay. So proof of 1. In the case that S star is a real number, you say, well, look, we know that we saw last time that the set of subsequential limits was closed, right? That E was closed, right? That if you're a limit point of the set of subsequential limits, well, then you are yourself a subsequential limit. Okay. So suppose that well, okay, so there's sort of like, suppose that S star is not in E. Okay. Suppose S star is not in E. Okay. Well, this thing, right, remember that S star is the supremum, right, of the set of subsequential limits, right? Well, if it's not in there, in that case, S star must be a limit point of the set of subsequential limits, right? Remember we had this, we said this last time, that if you have the supremum of some set, right? You have the supremum of some set, and it's not in the set, right? That means that given any epsilon, right? Given any epsilon, there must be somebody from the set inside there, right? So you can construct that's exactly saying that this thing is a limit point, right? Right? Because you see that the punctured neighborhood contains somebody. This punctured epsilon neighborhood must contain somebody from the set, right? We saw last time that if supremum of E is not contained in E, right? Is not contained in E, then every neighborhood of the supremum, every punctured neighborhood intersect the set is non-empty. Okay. Right? But E prime is part of E, right? Because E was closed, right? So this leads to contradiction, right? If you're not in E, then you are in E, right? If you're not in E, then you must be in E. Okay, so contradiction. Okay. So that shows that the lim sup has to be one of the subsequential limits. Okay, if S star were infinite, then you'd say, well, look, that tells me that E has no upper bound, right? E has no upper bound. Right? But if E has no upper bound, that tells you that that the sequence has no upper bound, right? It's not bounded above. Right? If the set of subsequential limits has no upper bound, well, then your sequence, of course, also has no upper bound. Right? But in that case, you can construct a subsequence S of nk that converges to infinity, right? You can construct a subsequence that converges to infinity. Right? Because, is that clear? Is that clear? Right? If your sequence isn't bounded above, right? If your sequence isn't bounded above, then that means that whatever n you choose, then your sequence jumps over it infinitely many times, right? If it jumped over it only finite many times, that would mean that after some point, it's all below that n, right? So not bounded above means that whatever n you choose, you jump over it infinitely many times, right? So in this way, I can construct a sequence of increasing indices. Right? I can construct a sequence of increasing indices that goes to infinity. Right? Should I write that out? You guys look kind of perplexed. Let me write it out. So, y. Sn not bounded above implies that given any n, there are infinitely many n such that S of n exceeds that number. Right? If not, you could show that your sequence was bounded above. Right? So so choose for each n in the natural numbers, choose n sub n such that S and n is bigger than n, and S and n is bigger than S and n minus 1. So you have, so that your indices are, such that n is bigger than n minus 1. Right? So that your indices are increasing. Right? And you can do this because there's you have infinitely many guys to choose from. Okay. And then your sequence is unbounded. Right? Then this S and n goes to infinity and with capital N. Unbounded.
So over there, when we say it converges to infinity,
Yeah.
from the way we defined like convergence of a sequence, I thought it would always have to be like the p prime that like a sequence could converge to. If we were to say it converges, it has to be something different than infinity.
Oh, but you remember last time we introduced this notion of converging to infinity? We said right at the beginning when we started talking about lim sup, we said if this sort of thing happens, then we say it converges to infinity. Okay, and the reason we're doing that is for this. Yeah. So initially when we defined convergence, that was only for finite numbers. Okay, but now we're throwing this in to make the theorems cleaner. All right.
At the bottom there on the left,
Yeah.
you're saying S sub n goes to infinity as big N goes to infinity?
Yeah. So the limit as big N goes to infinity of this is infinity. Yeah, so sometimes people just write the thing that goes to infinity here. Or sometimes they'll write like big N goes up to infinity or something. Anyway, whatever you like. Okay. Okay, let's go on. Kind of going slower than I hoped. Okay. So, okay, part 2, right? Proof of 2. Okay. Why is it true that for any x bigger than this, there must be some n such that this happens? Suppose it doesn't happen, right? Suppose there exists an x bigger than lim sup Sn, and no matter what n you choose, there exists some n bigger than n such that Sn is actually greater than or equal to x. Okay, so suppose this doesn't happen, right? So proof by contradiction. Right. You've got your x, and suppose that right, no matter what n you choose, you fail, right? There's some number such that S of n is greater than or equal to x. Okay. Well, in that case, right, and this S is bigger than the lim sup, right? Bigger than the lim sup. But in that case, then there would be infinitely many n such that Sn is bigger than x. Right? Because we're saying no matter what n you choose, there's somebody bigger than that where the value exceeds x. Right? So there would be infinitely many indices. But that means that there exists a subsequential limit that is bigger than equal to x. Right? Because you're going to have infinitely many of these guys who are higher than x. Right? Here's x, and you've got infinitely many of the S of n's. Right? You've got infinitely many of the S of n's up here. Right? Well, either they're bounded, in which case they're going to converge to, there's going to be a convergent subsequence, right? Or they're unbounded, in which case you get infinity. Right, so in either case, you're going to get either a finite subsequential limit or an infinite subsequential limit that's bigger than x, right? But this thing was supposed to be the supremum, right, of the subsequential limits, right? So that's a contradiction. We'd have somebody in E, right? We'd have somebody in E that was, strictly greater than the supremum of E. That's contradiction. Abel, what is it?
So if the limit superior is the biggest of all the subsequential limits,
yes,
then I feel like couldn't we say like for all n?
For all n, everybody's going to be smaller than that? No, because so suppose you have a sequence that looks like this. Okay, the lim sup is 1. Okay. But now I'm going to throw in some guys at the beginning. Okay, I throw in some guys at the beginning. I can't say that everybody lies, So it is true that so here's the limit here's the S star, right? It's true that if I add on something to S star, then I can find a time past which everybody's underneath that line. But I can't guarantee that everybody's underneath that line, right? Because I can always throw in whatever I feel like, some finite messiness at the beginning. Anybody else? Any other questions? Okay. So let's go on to the last part. That there's only one such number, so uniqueness. Suppose that there are two numbers, right? Suppose that P and Q both possess properties 1 and 2. Okay. Well, you immediately run into a contradiction. So it's like this, right? Here's P and Q. Suppose without loss of generality that P is less than Q. Well, just use property 2, right? You say, well, look, I'm going to take my epsilon to be half the distance from P to Q. Then I know that there's some point past which everybody lies, all of my S of n's lie underneath there, right? Well, if all my S of n's eventually lie underneath here, then there's no way that Q can be a subsequential limit, right? Because you can't have a subsequence that converges to Q if past some point everybody is far away from Q. right? Everybody stays away from Q. There's no way that that guy is a subsequential limit. Okay, so that's the picture. So I'm not gonna write that down. That should be clear enough. Any questions? Yeah, Susan.
So the conclusion is that P is Q?
So P must be Q.
Okay.
Yeah. So right, if P is less than Q, then choose then for any x such that P is less than x is less than Q, we know that there exists an n such that if you're past that n, all s of n are less than x, right? But then Q cannot be one of the subsequential limits. Contradiction with 1. So this is a really nice characterization of the limb soup. Some of you may have seen some other characterization of the limb soup. You took like Math 101 before. That may show up on your homework. Okay. Okay, so just a couple of simple examples of sequences. So I'm not going to do too much of this, but maybe I'll do 2 examples. Okay, so the first is that the limit of P to the 1 over n is 1 as n goes to infinity for all P greater than 0. And the main reason I'm doing this is to show you a particular trick. Okay. Okay. So we do this in the case where P is greater than 1. The case where P is less than 1 follows from the first case, actually. Okay, so this is just to show you something funny, or something kind of handy. Okay, so we want to show that the limit of P to the 1 minus 1 over n minus 1 is 0, right, as n goes to infinity. Okay. Right, or I should say, it suffices to show this thing, right, of course. Okay, so let's call this thing x sub n. Okay. So let's call this difference x sub n. Okay. So x sub n, 1 plus x sub n, P to the 1 over n minus 1 is x sub n. In other words, if I take x sub n and I add 1 to it, and I take that to the nth power, I get P. So notice 1 plus x sub n to the n is P. Okay, and we're trying to show that x sub n goes to 0. So, okay, so we use the binomial theorem. We use the binomial theorem to get information about x sub n. Okay, so recall the binomial theorem that if you take something of the form 1 plus x to the n, that's the same thing as summation n choose k, x to the k, as k goes from 0 to n. right? Where n choose k is n factorial over k factorial n minus k factorial. This is binomial theorem, right? You saw something like this when you're a kid and you were introduced to Pascal's triangle, right? Right. If you take like 1 plus x, you take 1 plus x squared, 1 plus x cubed, right? Right. 1 plus x squared is 1, right? Plus 2x plus x squared. You get 1 plus 3x plus 3x squared plus 1x cubed, and so on and so forth. Right? You get the coefficients are form so-called Pascal's triangle, right? The binomial coefficients. Okay. So we use the binomial theorem, and we say, okay, well, look, this thing here, right? 1 plus x of n to the n, that's equal to p, right? But this 1 plus x of n to the n is bigger than or equal to 1 plus n x of n. By the binomial theorem, right? 1 plus x to the n is equal to 1 plus nx plus some other stuff, right? 1 plus nx plus some other stuff, right? So 1 plus nx is going to be smaller than that, right? It's going to be smaller than that. Okay, so by the binomial theorem, we get this, but that gives us information about x, right? That tells us that x of n is smaller than p minus 1 over n. Right? And, right, since p was bigger than 1, right, this p to the 1 over n is also bigger than 1. Right? And that tells us that x of n, which equals p to the 1 over n minus 1, is bigger than 0. Right? So we get this guy is bigger than 0. Okay. And then you notice that if you let n go to infinity, that tells you that x of n goes to 0, right? By the squeeze theorem, right? So as n goes to infinity, you know, x of n is trapped between this thing divided by n and 0, right? So it gets mashed to 0. X of n goes to 0. Okay, I think that's there's another example of using the binomial theorem in your book. This one, that if you take n to the 1 over n as n goes to infinity, then that tends to 1. Okay, and so I was going to do that as well, but I think there's no need for you to see the use of the binomial theorem 2 times. The only thing is that in this proof we don't use this factor. We actually use the second factor. Okay, we don't use this power 1 guy, but we use the power 2 guy. Okay, so okay. So now we switch to the second notepad. So that's all we're going to say about sequences. Now we're going to talk about series. Okay, so return to series. Right, you've all seen series before. But now we're going to do it from our new point of view, and you'll see why we care about the lim sup. Okay, so notation, right? You have some sequence, a sub n, a sequence, and you notate, if I write a sub n, no, a sub k, k going from p to q, right? You know what this means, right? This is the sum of the terms, right? This is going to be a sub p plus a sub p plus 1 plus all the way up to a sub q, right? This is just the standard series notation, right? Right? You're summing the indices as the index ranges from this lower index to this upper index. Okay, so now we define something called the sequence of partial sums. So again, a sub n is sequence, and the sequence of partial sums of a sub n is defined as, well, you just sum the a's from 1 to n. Okay. So you have a sequence, and then you create this thing called the sequence of partial sums, right? So, for example, if my a sub n is 1 over n squared, right, then my sequence of partial sums is the sum of the a sub n, sum of the a sub k, as k goes from 1 to n. Right? So it's going to be a1 plus a2 plus an. Right? You have a sequence, right? You have a sequence. Your sequence is sequence like this, right? And then you have the sequence of partial sums. The first, right? S sub 1 is the sum of the first term. S sub 2 is the sum of the first two terms. Right? S sub 3, the sum of the first three terms, etc., etc. Right? You take the sum up to the nth. Okay. S sub n is the sum up to the nth term. Okay. Does anybody know what this sequence tends towards? What the limit of the sequence of partial sums of the squares is? If you take 1 plus 1/4 plus 1/9 plus. So anybody know? It turns out to have a funny answer, which is pi squared over 6, I think. Yeah. But you won't understand how to get that until you take a course in Fourier analysis. I think that's pretty much the first time you'll see a proof of that. Okay. Okay, so think like this, right? Sequence, partial sum sequence, right? Now, if the partial sum sequence converges to some value s, we write the sum from 1 to infinity of a sub n equals s. Okay. And say the infinite series converges to s. Okay. 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 But you should always remember that this is a shorthand. Okay. It doesn't mean that if you sum all these numbers from 1 to infinity, you get s. It means that if you look at the partial sum sequence, then the partial sum sequence converges to s. Okay, this is a shorthand, right? Shorthand for for this, right? This thing is shorthand for partial sum sequence converging to S. Okay, so convergence of a series is really talking about the convergence of some sequence, okay? From some sequence, the sequence of partial sums. Okay. And so all that stuff that we did for sequences now applies to series, okay? So here's now we're just going to apply a bunch of the stuff that we just did. So translation of prior results to series, to the setting of series. Okay. Okay. So the first thing is recall that. Oh yeah. I'm sorry. So I should have said that all these sequences are sequences of complex numbers. Right? Because we're talking about adding things, right? It's not a sequence in an arbitrary metric space. What we're doing now is just sequences of complex numbers. Okay, because otherwise we can't talk about adding. Okay, so okay, so so recall that that C is complete, right? So a sequence converges if and only if it's Cauchy, right? If and only if it's Cauchy. Okay, so this gives us the theorem about series called the Cauchy criterion. Cauchy criterion for convergence of sequences. Convergence of series, excuse me. Okay, this is pretty cool. It says that a series converges if and only if given any epsilon, there exists a time such that for all m and n bigger than n, the absolute value of the sum from n to m is smaller than epsilon. Yes, Susan.
What's the name of this theorem again?
The Cauchy criterion. The Cauchy criterion. The Cauchy criterion. Cauchy is the same Cauchy as in Cauchy sequences. Criterion for convergence of series. Sorry. For convergence of series. Okay. Okay. So remember, what does Cauchy mean? What does Cauchy mean? A sequence is Cauchy if what? If all the terms get closer to each other, right? So like given any epsilon, you can find a time past which all differences are smaller than epsilon. Okay? So let's think about that, right? So here's the proof. You say, well, look, A sub n converges is the same thing as saying that the sequence of partial sums of partial sums converges. Right? The sequence of partial sums converges. Right? But sequence of partial sums converges means that given any epsilon, there exists, or maybe I should just slow it down, it means that this sequence is Cauchy. right? Sequence converges if and only if it's Cauchy, because we're in a complete space. Okay. But that's the same thing as saying that given a epsilon, there exists a time such that if we're past that time, then S of m minus S of n is smaller than epsilon. Right? In absolute value.
For the summation, is it infinite?
Yeah. Yeah. The series converges if and only if the sequence of partial sum converges. Right? Well, since we're in a complete space, that's if and only if the sequence is Cauchy. That's this. Cauchy means this. Right? But and let's assume that m is bigger than n, just to make it neat. Okay. Well, what's S of n minus S of n? Right? It's the sum up to the nth term minus the sum up to the nth term. Right? But what is that? That's going to be, this is the sum from k equals n plus 1 up to n of a sub k. That's the Cauchy criterion. Right? Okay, so all we've done is just nothing. Right? All we've done is just restate the Cauchy criterion in the setting of series, right? Edward.
Did you drop a n plus 1 when you stated the theorem? At the bottom for all.
Yeah, but you see, it doesn't matter because I can take my n to be 1 smaller. Right, I'll take my n to be 1 smaller. This plus 1 doesn't affect the result. Right? If I can show that I can always get this thing smaller than epsilon, certainly I can I can show that. Yeah. Right. I just shift it down one, basically. Okay. Okay. So so all we did was say a series converges if the sequence of partial sums is Cauchy, right? And that gives us this criterion. Well, this is just a direct translation of saying, right? This is the same thing as saying S of n is Cauchy. Right? This thing converges if and only if the sequence of partial sums is Cauchy. That's the Cauchy criterion. Okay. So, yeah. Okay. 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 So one remark is that, of course, we could take n to be m minus 1. Okay. And that would say that the sum, to be m itself. Okay. We take m to be equal to n. N and m to be the same. Okay. In that case, what we're saying is that there's a time past which S of m is smaller than epsilon. Right? Right. So that says that for all epsilon greater than 0, there exists a time such that if n is bigger than that time, then the absolute value of S of n is smaller than epsilon. Right? That's the same thing as saying that the limit of the S of n's must be 0. Abba.
When we say take n to be m
Yeah.
in this equation,
In here, yeah.
wouldn't that be the absolute value? There's two terms in the absolute value. Right?
Oh, I'm sorry. M minus 1.
Oh.
Thanks. It was right before. Okay. So now let me change these guys to M's. Okay. So notice that if you converge, then you know that the limit of your terms. What am I doing? What am I doing? That should be A sub n. Sorry. Yeah. Because we sum up to the A sub nth term, and we subtract the sum up to the A sub nth minus n minus 1th terms. And so we're left with the A sub nth term. Okay. So this is the so-called divergence test, right? The nth term test, right? If your sequence converges, then you know that the terms must that the terms must go to 0. Right? This is so-called nth term test that you learned in calculus, also called the divergence test. Right? If the terms don't go to 0, well, then you can't converge, right? Because convergence would imply that the terms go to 0. Everybody all right? Okay.
Why are we taking n to be n minus 1?
So we know it's true for any n and m bigger than n, right? So I'm just going to take my n to be m minus 1.
And then you get s of m minus s of n minus 1.
Right.
Its absolute value is less than epsilon.
Right.
How does that translate to a sub m?
Well, what's S of m? S of m is the sum up until the mth term of the a sub k's, right? And you're subtracting up the sum up to the n minus 1th term of the a sub k's, right? So what are you left with? Well, you're left with only the top term, right? Because you subtracted all the preceding terms,
Thank you so
right?
much.
And so that gives you the a sub m, right? So the a sub m must be smaller than epsilon, right? And so you know that the terms go to 0. Other questions? Okay, so that's one sort of simple application of our previous theory. Okay, another simple application is using the monotonic sequence theorem on non-negative series. So here's the theorem about non-negative series. Okay. So suppose you have a non-negative sequence. Suppose you have a non-negative sequence, and let S of n be, again, the sequence of partial sums. Well, what can you tell me about the sequence of partial sums? These guys are greater than 0, right? And so when we keep on adding them on, what happens to the partial sums?
Keeps increasing.
It's going to be increasing, right? So we know that, right, this is going to be monotonically increasing. Right? Well, we know that a monotonically increasing sequence converges if and only if what? Next.
If it's bounded.
If it's bounded, right? Bounded above, yeah. Okay. So, so what's the theorem? The theorem is this: that the series converges if and only if the sequence of partial sums is bounded. Right. Since it's monotonically increasing, it'll be bounded below for sure. Okay. And we don't even need to prove it, right? We're done. Right? The proof is this thing is, is monotonically increasing, so it converges if and only if the sequence is bounded. Okay. So that's it for now. We're going to do, basically, for the next class or so, we're going to reconstruct all of your old series knowledge, but using the lim sup this time. Okay, the lim sup will be enough. Okay, I have homeworks to hand back. If you don't mind sticking around.
When is resolved?